So now let's go to a more advanced classification of the materials. We have 6 major classes. Let's start with the most easy concept to understand, the metals. So the metals are something which is characterized by a metallic bond. They have metallic appearance, meaning that the electrons are free to move in the surface of those elements, and they interact with the electromagnetic wave and absorb it or reflect it. The most important metal for the human activities is steel, which is a nanocomposite actually material, an alloy between carbon and iron. Of course, metallurgy is a huge field, and we may separate the ferrous materials from the non-ferrous materials, like for example copper, which is most important for wires and electrical connections, or gold for jewelry and for advanced electronics, or for example brass and all other metals that are used to realize small mechanical parts that has, for example, capability to withstand huge wears, or in other words, resistance to corrosion. We may have also alloys and superalloys, so to enhance the mechanical properties or the chemical resistance, it is very frequently added some element to the standard composition of a metal alloy. For example, in the case of aerospace applications, one of the most widely used alloy is that of aluminum, titanium, vanadium. Another application for the alloys is that of the engine blades in airplanes. Those are realized by intermetallic compounds. So intermetallic compounds are something quite different from the alloys. In the alloy, the composition may vary within certain limits, while in the intermetallic compound the composition is perfect. There is a perfect stoichiometry ratio between the components. For example, nitinol, which is a shape memory alloy, which actually has a very important property, that of changing shape depending on the temperature cycles that you submitted. Most importantly, has a perfectly matched stoichiometric composition. If you insert just even 1% more of one of the composing elements, you will end up that you will completely destroy the functional property that you have. Other intermetallic compounds have incredible resistance to cyclic mechanical action, and they are used in very peculiar engineering applications. The second major class of materials is that of ceramics, and within that class we may differentiate and also include the glasses. So ceramics are usually metal oxides, and they are usually characterized by extremely high melting temperatures, much higher than the corresponding metals. Of course, there are exceptions to these, and not only metal oxide but also mixed compositions are used, in particular for the engineering applications. Let me make an example. We have talked about sapphire and alumina, which is aluminum oxide, is one of the most important ceramic materials used for refractory applications, since the melting temperature is about 2000 degrees Celsius. So it is used to realize a certain kind of bricks, which are used to pave the inner part of melting pots. Another example is that of zirconia, which is zirconium oxide. This particular ceramic material has the capability of conduct very well ions, and in particular oxygen ions. So it is used to detect the oxygen amount level in a certain atmosphere, and in particular it is part of the lambda sensor that is placed in every engine in the car industry. This small part of the sensor is brought to a certain temperature where the diffusion coefficient of oxygen within the crystalline structure of zirconia is high enough to allow electrical detection and reading of the oxygen content. Other example of non-standard ceramic is that of silicon carbide. Silicon carbide is perfectly 50% compound between silicon and carbon, and it's one of the hardest materials that the man ever conceived. Of course, the hardest one is diamond, and we were able to synthesize, to make synthetic diamonds. But the silicon carbide, which is, by the way, less expensive than the synthetic diamond, is very, very tough, and it is used to make abrasion tools. So they realize small, tiny crystals of silicon carbide and disperse them into a metallic matrix. And those are used, for example, for drilling stones or concrete or wherever you need to have a huge wear resistance. Silicon carbide is also a very important material for electronic applications because well, it has an indirect band gap, but it has a huge resistance to high temperatures, meaning that you can realize electronic circuits using silicon carbide instead of silicon for the applications requiring resistance to higher temperatures, or where the current density that you are submitting through the device is so high that thermal heating by means of a Joule effect is affecting and could destroy a standard device realized by silicon. Other ceramics are the white wares. Of course, this is a very standard application for ceramics. There is nothing special in the sense that that technology was assessed 5,000 years ago, and still nowadays we have this technology which has not made any other progresses. The glasses are very important, not only for the windows and for all the applications where they are needed to have optical transparency but still keeping separate atmospheres. Glasses are very important for the fiber glasses, which nowadays are fundamental for the information communication technology compartment to transport laser beams and information at huge through-output rates. So the idea is that in the case of fiber glasses, you draw a material that is composed by a core and a shell, basically having different refractive indexes. So this difference in the refraction index creates the condition to confine an electromagnetic radiation and transport it through long distances without the need of amplifying it again. Another very important ceramic material for our industrial application is concrete. Of course, huge tons of concrete per second are produced all over the world and applied into the civilian buildings. Then another category of materials is that of semiconductors. Semiconductor may be classified as ceramics, but they have different properties and different applications in the sense that their main purpose is the interaction with electrons and holes and with electromagnetic waves, so light. In particular, the most important one is silicon, of course. There is germanium as well. 3,5 compounds are very important, like gallium arsenide, I told you, for the optoelectronic applications. And 2,6 compounds like zinc oxide, for example, is one of the materials that we have studied for a long time, which is a wideband semiconductor, meaning that it is able to interact with high energy electromagnetic radiation like the UV light. And it has also piezotronic effects, in particular a sort of piezoelectricity. Also photonic materials are very important, and I will show you later an example of the alloys that are used for those solid state lasers or LEDs. Another very important category is that of polymers, including both synthetic polymers and natural polymers. The concept is that we have a chemical structure that is a perfect repetition of a standard unit. The standard unit may have a carbon backbone, so the main chain is composed only by carbon atoms, and hydrogen, which is one of the most abundant elements in the polymers, and for example fluorine, chlorine as a pendant. Okay, So those materials are characterized by huge plasticity, by quite a low elasticity. So regarding mechanical applications, they are not very important, but they are extremely lightweight. So if you compute the engineering property and divide it by the weight of the structure that you have, polymers are overperforming certain times with respect to metals or ceramic materials. They are used widely as adhesives. This application is very important. So to join different parts, you can use the single components of the macromolecule, which is called monomer, and by certain means, like for example by submitting those monomers to a UV light or to a temperature gradient, you initialize a chemical reaction, which is called the polymerization, that welds together all the monomers, realizing the polymer. In this process, you are able to join mechanically different parts. Another example of natural polymer is that of wood, of course. Both cellulose and lignin, which are the main components, chemical components of the wood, are polymers of sugar or certain kinds of sugar. So you can imagine that the standard unit is repeated many times. The different trees, the different plants have each one a particular peculiar structure. So you may find out, for example, that hemp has the longest chains of cellulose, and that's why it was used in the past for making ropes and wires and clothes as well. Cotton is another example, of course, of vegetable which is able to provide us a good polymer through which we can achieve tissues and textiles. Then we go to the most advanced classes of materials, the composites. So composites are normally realized by mixing together, joining together two different materials of the previous classes we have seen. So for example, you may think of adding to a plastic material a metal. In which way? For example, adding wires to a polymeric matrix, you may achieve a huge resistance. Or you may use, for example, fiberglasses or a fiberglass tissue and insert it into a polymer. This would give you much higher mechanical strength along all the direction of the deformation of a two-dimensional material, for example. Laminates are very diffuse kind of composites. So you have, for example, in the case of wood, you have layers of wood which are aligned, keeping the direction of the fibers in different orientation, layer by layer. This will increase hugely the isotropic properties of the final laminate. Or we may think of placing together a piece of wood and a piece of polymer. That would give you enhanced properties, enhanced resistance to water, for example, or to scratch. Then we have the last category, which is that of smart or functional materials and advanced materials, which is the most intriguing one, in particular for those who work in the nanotechnology compartment, because it's something that never ends, and we already have a certain classification, sub-classification within the smart materials, but the progress in scientific research always brings you something new. In particular, I already told you about the shape memory alloys. So this is a very nice product, nowadays commercial. That means that we are able to realize a wire of a metallic like material, which is able to recover a certain shape by just going through a thermal cycle. Another very important material is the piezoelectric ceramic. This is used to transduce pressure into a voltage signal, or in the reverse effect, to transform a mechanical oscillation or solicitation into a voltage to generate energy. There is the equivalent of a piezoelectric effect, which is the magnetostrictive effect, where you have a variation of the volume of the crystalline cell with respect to the application of an external magnetic field. And this is used in commercial alloys, which are called terphenols. So terphenol D is the substance, the synthetic substance with the highest magnetostriction coefficient, meaning that it is possible with a small applied magnetic field to produce huge variations in its shape. And it is applied in linear engines. Another application for the magnetostrictive materials is that of the sensors. So you may transduce a variation of the magnetic field into a mechanical vibration. Or side effects, like for example the buzzer, the buzzing noise that you hear when you are close to a big, huge transformer for standard grid electricity, is due to the oscillation of the transformer bores at the same frequency of the grid.